So a set is a collection of well-defined objects. Each object is an element or member of the set. So many times sets are used to classify objects. So for example, are these well-defined sets? So the first one says the set of students taking Math 110. So this particular set is well defined because we would be able to figure out who all those students are. Any student that's enrolled in Math 110 would be a member or an element of that set. The second example is the set of young people. So the set of young people is not a well-defined set because everybody's definition of young is a little bit different. So we would consider the set of young people not a well-defined set. So the symbol, this little E, is a symbol for is a member of. And then E with a little slash through it is a symbol for not a member of. So let's take a look at example 2. So it says set A is a set of even numbers. So since 4 is an even number, we say 4 is an element of A. So this isn't the only answer because there's lots of even numbers. So we could say 8 is an element of set A. We could say 12 is an element of set A. Notice the way it's written, okay? I can't flip it around the other way because if I write it like this, A is an element of 10, that doesn't even make any sense. Set A cannot be an element of a number. So the order that you write your elements, that's going to be very important, okay? Since 3 is an odd number, we say 3 is not an element of A. So there's lots of examples here also. So 5 is an odd number, so 5 is not an element of A. Okay, 11 is not an element of A. And again, you cannot switch the order around because it wouldn't make any sense to say A is not an element of 5. So in example 3, set B is a set of multiples of 3 less than 32. So the multiples of 3 that are less than 32 would be 3, 6, 9, 12, etc. So it says name an element of set B. So I could say 15 is an element of set B. 15 is a multiple of 3. We could say 18 is an element of set B. 18 is a multiple of 3. So our next definition is subset. So a subset is a set that's part of some other set. So notice here that to be a subset, it also has to be a set. So that means we need to have set brackets around it if we're talking about subsets. So the symbol for subset is this little C, or you could use the C with a little line underneath it. Some books will use this for subset, and some will use this symbol. And then if you do not have a subset, you would use the C with a slash through it, or you could also use a C with a little line and a slash through it. So if we take a look at example 4, so example 4 gives us set A. Set A are the elements 2, 4, 6, 8, so the even numbers starting with 2, ending in 14. So the set 2, 6, the set 2, 6 is part of set A, so we would say it's a subset of set A. Notice I know I'm talking about a subset and not an element because I've got these set brackets. Notice the elements up here do not have set brackets. The set 310 is not a subset of A because notice the number 3 is not part of set A. So a few more definitions for you. So an infinite set is a set that goes on forever. So for example, the set of even numbers, this is an infinite set because a set of even numbers go on forever without bound. A finite set is a set where it has a particular number of elements where you can count the number of elements that are there. So in example 4, set A here, this is a finite set because I can count the number of elements that are here. And then for an empty set, we have a set that has no elements. So there are 2 symbols for our empty set. So this was in your reading. So the symbols could be set brackets with nothing inside. Okay, or you could do the circle with a slash through it. Both of those symbols will represent an empty set. The universal set, I'm going to talk a little bit more about that in a minute. So we're going to go ahead and hold off on that. All right, so there are different ways to describe sets. So we can describe sets in words. So notice in example 2, I described that set in words, okay, the set of even numbers. We can describe a set in list notation. So I described a set in list notation in example 4. Okay, and then we could also describe a set using set builder notation, and that's what I'm going to show you now. So example 5. So given set T is 15, 18, 21, etc. So notice the numbers are going up by 3. So if the numbers are going up by 3, then they're multiples of 3. So if I want to describe set T using words, I would say set T is the multiples of 3 starting with 15 and ending with 30. Notice you have to be specific, because if you just say multiples of 3 go on forever, right? And there are multiples of 3 also before the number 15. So make sure you're specific so the reader knows exactly what numbers belong in a particular set. So set B says part B of set says to describe set T using set builder notation. So every set builder notation is going to start this way. So you would name the set. So set T is equal to the set of all x's such that. So if I read this, I would say set T is the set of all x's such that. Okay, so again, set T is equal to the set of all x's such that. Okay. So if I want to write it as a multiple, so set T is equal to the set of all x's such that, notice each of these x values are multiples of 3. So x has to be equal to 3 times some number n. So I'm going to leave a comma and I'm going to leave a space. I'm going to come back and put something in there in a second. So back here, I'm going to write the numbers I want to use for n. So I'm going to go up to my set. The smallest number in my set is 15. So I'm going to ask myself, 3 times what number is 15? 3 times 5. So 5 is less than or equal to, n is in my formula, so n, which is less than or equal to. Now I'm going to go up. The largest number in my set is 30. So 3 times what number is 30? That would be 3 times 10. And then I'm going to close my set brackets. So this here is called a double inequality, and double inequalities are always written from smallest to largest. All right, and notice the numbers starting with 5 and ending with 10, and all the values between these would include decimals and fractions. Notice I'm not multiplying 3 by any decimal or fraction to get these outcomes up here. So in the center here, I've got to tell the reader what numbers I'm allowed to use for n. So in here, I'm going to say n is an element of the natural numbers. So this right here means that n is an element of the natural numbers. So when I add that into my notes, that's going to stipulate or minimize the numbers I'm allowed to use for n. So notice the natural numbers starting with 5 and ending with 10 would include 5, 6, 7, 8, 9, and 10 only. So notice the way it would work. So the first number I'm allowed to use for n is 5. 3 times 5 is 15. Notice 15 is in your set. Then I can use 6 because I'm only allowed to use the naturals. 3 times 6 is 18. Notice 18 is in your set. Then I'm going to use 7. 3 times 7 is 21. 21 is in our set. We'd use 8, 9, and then the last one I'm going to use is 10. So 3 times 10 is 30. 30 is in my set. Okay, so set T using set builder notation. All right, I'm also going to write it as divisible by. So T is equal to the set of all x's such that all of these numbers are divisible by 3. So x over 3 has to be an element of the naturals. So what this is saying is that if I take any of the numbers and I divide by 3 and my outcome is natural, then that number belongs in my set. So the numbers I have to check to see if they're divisible by 3 start with 15. Okay, notice x is in the formula this time, so I'm going to put x in the middle, and it ends with 30. So the way this works is I'm going to first start with 15. So 15 divided by 3 is 5. 5 is a natural number, so 15 is divisible by 3, so 15 belongs in the set. I'm going to try 16. 16 divided by 3, that would have a remainder. So anytime I get a remainder, the outcome is not natural. Notice 16 is not in my set. I'm going to try 17. 17 divided by 3 gives me a remainder. So notice that would not be a natural number. So 17 doesn't belong in the set. Then I'm going to try 18. 18 divided by 3 is the natural number 6. So 18 is divisible by 3. So 18 belongs in my set. And I'm going to check all my numbers until I get up to 30. Okay, each one that's divisible by 3 would go into the set. So let's try one more example together. So given set A, so set A is the set of all x's such that x is equal to 5 times some number n is an element in the naturals, 7 is less than or equal to n, which is less than or equal to 12. So it says describe set A using list notation. So when I list it, I'm going to say set A is equal to the set. All right, first number I can use for n is 7. So 5 times 7 is 35. 35 belongs in my set. Then I can try 8. 5 times 8 is 40. 40 belongs in the set. I'm going to try 9. 5 times 9 is 45. 45 belongs in the set. I'm going to try 10. 5 times 10 is 50. 50 belongs in the set. I'm going to try 11. I'm down here. 5 times 11 is 55. 55 belongs in the set. And then the last number I could try is 12. So 5 times 12 is 60. 60 belongs in the set. And I'm going to close my set brackets. So last for example 5, or example 6, I should say, describe set A as divisible by and set builder notation. So notice all these numbers are divisible by 5. So set A is the set of all x's such that x divided by 5 has to be an element in the naturals. The numbers I have to check are starting with 35. Notice x is in my problem, so x less than or equal to ending in 60. Close my set brackets. All right, I'm going to leave example 7 for you to try. Okay, and the last thing I'm going to talk about here are our definitions. So first definition, intersection of sets A and B, written as A intersect B, consists of the set of all elements common to both sets A and B. So if I wanted to draw a picture of this, I'm going to start with my universal set. I have a circle for set A. I have a circle for set B. So A intersect B consists of the set of all elements common to both sets A and B. So I'm going to shade the common area. So there's my intersection. So A intersect B. So the key word for intersection is the word and. Next, we have definition of union. So union of sets A and B, written as A union B, consists of the set of all elements that are in set A or B or in both sets A and B. So again, drawing my Venn diagram, I have a circle for set A. I have a circle for set B. So the union consists of, again, a set of all elements that are in set A, so anything in A, okay, or in B, so anything in B, or in both. Notice both is already shaded. So A union B, so it has a keyword or. Those keywords are going to come into play when we do our word problems. Last definition, the complement of set A consists of all elements in U that are not in A, written as A complement. So again, I'm going to draw my Venn diagram. I only have one set this time, set A. So it's going to consist of all the elements in our universal set. So inside the rectangle that are not in set A. So I would be shading everything outside of my circle. That would represent the complement. So A complement has a keyword not.